Alright guys, so here is your example that you wanted for doing the limit definition of the definite integral. That's what it's actually called, generating this actual value. So I've set some stuff up prior to, so if you want to get this in your notes, feel free to pause it as we go along, but I'll try to explain it in a slow enough fashion. So first thing is right here, we're dealing with a quadratic x squared plus 2x plus 5. So that's going to be our f of x, and we're going to deal with the left and right boundaries of 1 and 6 for our curve. So again, we're looking below the x squared plus 2x plus 5 curve between 1 and 6 and the x-axis. And what I first wanted to do was use the evaluation theorem to show what my answer should be when I get it. So I've gone ahead and computed big F of x, the antiderivative of x squared plus 2x plus 5, and I did not forget my plus c. And I evaluated it at its endpoints at 6 and 1. So you'll see that f of 6 ends up being 138 plus c. F of 1 ends up being 19/3 plus c. And the evaluation theorem says evaluate and then subtract f of b minus f of a. So f of 6 minus f of 1. And I do the subtraction and I get 395/3 or 131.666 repeating. So when I go and do the limit definition, this is what I expect to see for my numeric answer at the end. Alright, so now let's get into doing some work. So same function, same domain up at the top. The first thing we want to do is define our delta x. And we said the delta x is always b minus a over n, so 6 minus 1 over n. So for this particular problem, delta x is going to be 5 over n. The other thing is, how do we define x sub I? Well, x sub I is simply your starting point plus I times delta x. So, maybe writing it as x sub 0 plus I times delta x. Well, our x sub 0 value ends up being our left bound of 1 plus I times delta x, which is 5 over n. So I'm going to go ahead and say that x sub I is 1 plus 5i over n. So these are the two most critical pieces to using the limit definition, because as you see in the formula down here, delta x appears out in front of the summation, and we need to figure out what f of x sub I is, so clearly x sub I is going to be a big deal. So those are going to be the two expressions that we're going to use in place of delta x and x sub I in our limit definition. Alright, time to get to work. So on the left hand side, I have the limit definition written out with my x sub I inserted where the x sub I was and my delta x inserted where my delta x was. On the right hand side, I'm just giving myself a little bit of workspace with the original function x squared plus 2x plus 5. You'll see why in a second. So the first thing that we have to do is we have to substitute in a 1 plus 5i over n everywhere we see an x in this function. So I'm really looking at the limit as n approaches infinity of 5 over n. I won't even talk this all out because I imagine you're going to hear me say it about 400 times if I do. F of x sub I is going to be 1 plus 5i over n squared. There's the x squared term, plus 2 of those, so plus 2 plus 5i over n plus 5. And again, that came from substituting in x sub I here and here, and there's no need to substitute it in at the end because 5 is just a constant. That particular term is pretty crazy right now, this over here. So what I want to do is actually take, and over here in my little scratch space on the right, I'm going to expand that for you. So the first piece I'm going to expand is the 1 plus 5i over n squared. So 1 plus 5i over n squared. Well, 1 plus 5i over n squared oh, excuse me, is 1 plus 10i over n, because I have two 5i over n's, and then plus 5i over n squared, which is 25i squared over n squared. So that's that piece. Then I have the 2 times 1 plus 5i over n. So 2 times 1 plus 5i over n. Well, that one's not too hard. That's just a distribution to 2 plus 10i over n, and then plus 5. So I have this piece here, I have this piece here, and then I just got a plus 5. So let's do some combining of like terms and rewrite this. So this is the limit. As n goes to infinity, 5 over n, the good old summation from 1 to n. And I have a 25i squared over n squared term. That one's gone. I have 10i over n, 10i over n. So I have 20i over n. And then I have a 2 and a 5, which is going to give me a 7. Oh, a 2, a 5, and a 1, which is actually going to give me an 8. The next thing I want to do here is pull out anything that doesn't change with the summations. And actually, maybe even before doing that, writing the individual summations themselves. I'm not going to rewrite the limit as n goes to infinity every single time. It gets a little old. I don't want to forget about 5 over n, though, so I've got to keep that. So I have the first summation is the summation for 25i squared over n squared. And 25 over n squared does not change. Again, that is unaffected by I. So I'm going to pull that out, and I'm left with an I squared. My 20i over n term has a 20 over n that doesn't change. And I'm just left with an I here. And then summation of I equals 1 to n of 8. Alright, so I've broken this down into its individual pieces. And you can see now that my first term is simply in terms of I squared. My second term is in terms of I. My third term is in terms of a constant x. I'm going to go on to the next page and give myself a little bit more working room. Oh, by the way, sticking down here in the bottom, just as we remember, this is the number we're looking for, 131.666 repeating. All right, so that's what we ended with on the last screen. Let's go through a couple more steps. It's time to get rid of the i's. Let's get i's in terms of n. Oops, need a pen to do that. So again, I'm not going to rewrite the limit, but I got a 5 over n, 25 over n squared, and now I have the summation of I squared. And we know that the summation of I squared is simply n times n plus 1 times 2n plus 1 over 6. That's our summation substitution. Add to that 20 over n times I. Well, we know I is n times n plus 1 over 2. And Lisa will be happy. I'm just going to go straight to an 8n on the last one because the summation from 1 to n of a constant is just a constant times n. From here, this really becomes an algebra problem. It's about canceling and simplifying. So one of the first things I'm going to do is cancel my exponent down here with one of these n's, the same we did in class. I'm going to do that over here too. This n and this n are going to cancel out. And I'm going to see what I have left. Let's see here. That's a 5 over n on the outside. 25 over n times, now n plus 1 times 2n plus 1 is 2n squared plus 2n plus n, which is plus 3n plus 1 over 6. So that's that. Then I got 20 times, and actually, you know what? Let me get rid of that 20. Go away. Let's cancel the 20 and the 2 and make that a 10. So that would be a 10n plus 10 plus the 8n at the end. So it's 5 over n times 50n squared plus 75n plus 25 all over 6n. So that's the first two terms multiplied together. And then just combining like terms, it looks like I have 18n's and then a lonesome old 10. Getting there. Remember, we're looking at the limit as n approaches infinity of this, hoping that it's going to come out to 131.666 repeating. All right, we're almost there. So I guess probably the next thing that we should do is get a common denominator of 6n. And for this one, I am going to keep the limit because we're getting close. So this is 5 over n. And I want to write this all over 6n. So the 50n squared plus 75n plus 25. So to multiply, to get a denominator of 6n for 18, I'm going to multiply by 6n. That's going to give me a 108n squared, and then a 60n for the last term. And it looks like we can combine some like terms. So I have 108n and a 50n, so 158n squared. 75 and 60 is 135n plus 25 all over 6n. And now it's about time to go ahead and distribute that 5n inside the parentheses here. So that's the limit as n goes to infinity. So 5 times 158, carry the 2, divide by 3, subtract 9, 790 n squared plus 675 n plus 125. All of that over 6n times n, or 6n squared. We're taking the limit as this thing has n go to infinity. So essentially we know that those two terms over there at the right, the 675n and the 125, those things are just going to 0. Because when you divide through by n squared, they take off and go to 0. When I take and divide the n squareds out, I'm left with 790 over 6. Guess what? 790 over 6 is 131.666 repeating. Holy cow, you look at that. That's exactly what we expected it to be. So what that shows is that using the limit definition of the derivative, we get the exact same answer as we did by using the definite integral by ways of the evaluation theorem, which is one part of the fundamental theorem of calculus. So that's how you go about doing those problems. Again, it's just about organizing and substituting and being tidy. You know, use plenty of paper. Don't forget your limit at the end. Don't forget your 5 over n, your delta x at the beginning. If you follow all those basic steps, you should be able to get your answers. And you know what? If you get your answers, hopefully that will make you feel happy.